In November 2020, Apple put a laptop chip inside a MacBook and it outperformed Intel's best desktop processor. Not in one benchmark, not in a cherry-picked test. Across the board, video rendering, machine learning, raw compute throughput, a chip designed to run on battery power, in a thin aluminum laptop, beat a chip that required a tower computer with active cooling and a dedicated power supply, drawing 125 watts from the wall. The MacBook chip used 10. That gap is not a rounding error. It is not clever marketing. It is the result of a decade-long engineering decision that Intel dismissed, then ignored, then failed to copy. And once you understand how Apple did it, you will never look at computer hardware the same way again. Here is why that matters beyond benchmark bragging rights. Every laptop you will consider buying in the next 3 years will be shaped by this architectural shift. Every company building AI infrastructure, every software team deciding what machines to standardize on, every chip designer at Qualcomm, Microsoft, and Google, all of them are now chasing what Apple proved possible in 2020. The semiconductor industry, which drives somewhere north of $600 billion in global annual revenue, reorganized its roadmap around this event. Intel's market capitalization fell from roughly $250 billion in early 2020 to under $100 billion by mid-decade, a loss of wealth larger than the GDP of most countries. That destruction of value was not caused by one bad product. It was caused by Intel betting on the wrong architectural philosophy for 15 years, while Apple quietly built a different kind of machine entirely. For consumers, this means the computer you buy today will perform work that used to require professional workstation hardware, costing 5 times as much. For professionals in video, music, software development, and data science, it means the bottleneck that defined your workflow for years has effectively been eliminated. The question is whether you understand why, and whether you can see where this is going next. To understand what Apple did, you need to go back to the early days of mobile computing and a fundamental disagreement about what a chip is supposed to optimize for. For most of the history of personal computing, the goal was simple: maximize raw clock speed. The faster a processor could cycle through instructions, the faster your computer felt. Intel built an empire on this philosophy. Their x86 architecture, which dates back to 1978, was designed for performance first, efficiency second. It worked brilliantly for decades. But around 2005, a problem appeared. Chips were getting so fast and generating so much heat that engineers hit what became known as the power wall. You could not simply keep adding transistors and raising clock speeds without the chip melting itself. Intel's answer was to add more processor cores, more parallel lanes, same basic architecture. Meanwhile, a British company called ARM Holdings had been designing chips with the opposite philosophy since the 1980s. ARM stood for Advanced RISC Machine. RISC stands for Reduced Instruction Set Computing, which means the chip handles a smaller vocabulary of simpler commands, executes them very efficiently, and uses far less power doing it. Think of it like the difference between a Swiss Army knife and a surgeon's scalpel. Intel built increasingly elaborate Swiss Army knives. ARM designed scalpels. When smartphones arrived and battery life became critical, ARM's scalpel won that market entirely. Apple had been using ARM-based designs in the iPhone since 2007. By 2013, with the A7 chip, they were designing their own custom ARM processors in-house. They spent 7 years learning, iterating, and optimizing on hundreds of millions of iPhones before they ever put an ARM chip in a computer. The first revelation that most people miss is that Apple did not just port an ARM chip into a laptop. They redesigned the entire memory system from the ground up, and that is actually where most of the performance came from. In a traditional Intel-based computer, the processor and the RAM are separate components connected by a communication pathway called a memory bus. Data travels from RAM to the CPU, gets processed, travels back. This handoff creates latency, delay, and in a modern workstation handling large tasks, the processor often sits idle waiting for data to arrive. It is like having a brilliant chef in a kitchen where the refrigerator is in a different building. You can make the chef faster, but if every recipe requires a 10-second trip to retrieve ingredients, the overall throughput does not improve proportionally. Apple's M1 chip, released in November 2020, introduced what they called Unified Memory Architecture, or UMA. The CPU, GPU, and RAM are all on the same physical piece of silicon, sharing one memory pool with one unified cache hierarchy. Data does not travel between components. It simply exists in the same location that every processor core can access simultaneously. The memory bandwidth on the base M1 chip was 68.25 gigabytes per second. A comparable Intel system at the time offered around 50 gigabytes per second, and that data still had to cross a physical bus. The M1 Ultra, released in 2022, achieved 800 gigabytes per second of memory bandwidth. For context, that is roughly equivalent to transferring the entire contents of a standard laptop hard drive every 3 seconds. When you render a 4K video on an M1 Mac, the chip is not shuttling data back and forth between a CPU and a GPU and a separate RAM module. It is all happening in one unified space, with every core pulling from the same pool instantly. That architectural change alone accounts for a substantial portion of the performance gap. But it is not the whole story. The second revelation goes deeper, and this one overturns a belief that Intel itself held for decades. The assumption was that general-purpose processor cores are the most efficient way to handle computation. If a core can do anything, you can throw any workload at it, and it will handle the job. Intel optimized relentlessly within this framework. Apple rejected it. The M1 chip contains not just CPU cores and GPU cores, but a collection of highly specialized processing blocks, each built to do one specific job at extreme efficiency. There is a dedicated neural engine, a block of silicon that does nothing except run machine learning operations. On the M1, it runs at 11 trillion operations per second. There is a dedicated media engine for encoding and decoding video, which means playing or exporting a 4K ProRes video file consumes almost no CPU cycles because a purpose-built piece of hardware handles it entirely. There is a dedicated image signal processor, a dedicated security enclave, and dedicated hardware for Bluetooth, Wi-Fi, and display output. In a traditional PC architecture, all of these tasks compete for cycles on general-purpose CPU cores. On Apple Silicon, they each have their own dedicated hardware lane. The total transistor count on the M1 was 16 billion. Intel's comparable desktop chip at the time had roughly 10 billion in a smaller process node. Apple did not just win on transistor count, though. They won on allocation, putting silicon where it produced the maximum useful output per watt. This is the insight that changes how you think about chip design forever. Bigger is not better. More specialized is better. Every computational task that moves off the general-purpose CPU and onto dedicated hardware makes the whole system faster, cooler, and more efficient simultaneously. The implications for everything from laptop battery life to AI inference speed to data center energy costs are enormous. The mechanism that makes all of this possible comes down to manufacturing process and systems on chip design, and understanding both will make the whole picture click. Apple designs their own chips, but does not manufacture them. They contract fabrication to TSMC, the Taiwan Semiconductor Manufacturing Company, which operates the world's most advanced chip fabs. In 2020, TSMC manufactured the M1 on a 5-nanometer process, meaning the individual transistor features are 5 nanometers wide, roughly the diameter of 20 silicon atoms. Intel's manufacturing in the same period was struggling on their 10-nanometer process, which was effectively comparable to TSMC's 7-nanometer. The smaller the process node, the more transistors you can fit per square millimeter and the less power each one requires to switch. Apple had a manufacturing advantage measured in one full generation of chip technology, and they used it to pack more dedicated processing blocks onto a single die than Intel's process could accommodate. The result is what engineers call a system on a chip, or SoC. On a traditional PC motherboard, the CPU is one component, the GPU is another, the memory controller is another, and various specialized chips handle audio, networking, and security. Each of these communicates over standardized interfaces with built-in overhead. On Apple's M1, every one of those functions is integrated on a single piece of silicon, connected by internal buses running at speeds that external connections can never match. It is the difference between offices in the same building connected by hallways versus offices in separate buildings connected by roads. Latency drops, bandwidth explodes, and power consumption falls because data no longer has to be re-encoded and decoded at each interface crossing. The engineering elegance here is genuine. Apple did not find a magic trick. They made a series of decisions: build your own chip, own your software stack, manufacture at the leading edge, integrate everything. That each individually made sense, and combined into a result that looked like magic to anyone who had not been watching the pieces fall into place. The complications are real, and they deserve honesty. Apple's architecture only performs this way because Apple controls both the hardware and the operating system completely. Every efficiency gain in the unified memory architecture, every optimization in the neural engine, depends on macOS and Apple's first-party software being written explicitly for this design. Third-party software running through Rosetta 2, Apple's translation layer for x86 apps, does not get the full benefit. When the M1 launched, a significant portion of professional software had not been recompiled for ARM. Adobe's full Creative Suite took over a year to transition. Some enterprise software still runs in translation mode, as late as 2026. There is also a ceiling problem. Unified memory architecture means your memory is fixed at purchase. You cannot upgrade RAM after the fact, because it is soldered directly to the chip package. A base M1 MacBook shipped with 8 GB of unified memory. At the time, 8 GB of the kind of high bandwidth, on-die RAM Apple was using cost significantly more to produce than 8 GB of standard DDR4. Critics argued, with justification, that Apple was charging premium prices for configurations that should have started higher. A professional buying a base model Mac and later finding it insufficient cannot simply add more RAM the way a PC builder can. The repairability and upgradeability that defined PC ownership for 30 years does not exist in this architecture. And for enterprise IT departments managing fleets of thousands of machines, the inability to standardize on upgradable components creates real procurement complexity. These are not small problems. They represent a genuine philosophical trade-off between integrated performance and user flexibility. What this means for you personally depends on what you do, but the impact is broader than most people realize. If you work in video production, music, software development, or data science, you are already living inside the performance shift that Apple's M1 created. The workloads that used to require a Mac Pro tower costing $6,000 now run on a MacBook Air costing $1,500. That is not a minor convenience. It changes who can enter your field, what tools become accessible to independent creators, and how much of your working capital you need to spend on hardware. By mid-2026, with the M4 generation now shipping and the iPhone 18 Pro Max reportedly featuring an A18 chip built on TSMC's second-generation 3nm process, the performance gap over x86 has only widened. Qualcomm's Snapdragon X Elite chips brought ARM performance to Windows machines in 2024, and Microsoft's Copilot Plus PCs represent the industry's attempt to follow Apple's blueprint. This means the x86 monopoly on serious computing is functionally over. Within 2 years, every major laptop platform will be ARM-based. If you are a software developer, the choice of which architecture to write and optimize for is no longer theoretical. ARM is the primary platform. If you manage technology purchasing for a company, the 5-year total cost of ownership calculation for workstations has changed, because performance per watt affects electricity costs at scale. And if you are simply someone choosing a laptop, the performance tier you can access at a given price point in 2026 is fundamentally different from what existed in 2019. Zoom out far enough, and what Apple did between 2013 and 2020 looks less like a product launch and more like a controlled demolition of an assumption. The assumption was that general-purpose computing, endlessly faster cores running an endlessly complex instruction set, was the only path to performance.